Welcome to Chapter 11, Part 2, Similarity Measures. In this section, we will explore how to gauge whether a group of observations is similar or dissimilar to one another. Let's get started. Similarity measures help identify observations that are similar to each other or close neighbors in the k-nearest neighbors algorithm. Cluster analysis finds similarities among observations in the data and groups them into meaningful clusters based on similar characteristics. Clusters are formed so that observations are similar within a group but dissimilar across groups. Similarity measures are based on the distance between pairwise observations, records of the variables. A small distance implies high similarity, while a large distance implies low similarity. Let's look at some examples. Consider three observations on two variables. In the following table, read 8x1 as x sub 1 and 8x2 as x sub 2. Euclidean distance is widely used and measures the distance between two observations. Manhattan distance, on the other hand, is the shortest path for a vehicle to follow, measuring the shortest distance horizontally or vertically between observations. The Euclidean distance is more influenced by outliers than the Manhattan distance.
Let's calculate and interpret the Euclidean and Manhattan distances for our example.
To calculate the Euclidean distance between observations 1 and 2, we take the difference between x sub 1 and x sub 2 for observation 1 and square it. We do the same for observation 2. Then these squared differences are added together and we take the square root of the result to find the Euclidean distance. To find the Manhattan distance between the same 2 points, we simply add the absolute value of the differences between the 2 points for each observation. For data with multiple variables on different scales, the scale of each variable can influence the distance measures. To ensure each value receives equal weight, we can standardize the data by computing a z-score or use min-max normalization to rescale each value between 0 and 1. Consider a sample of 5 consumers with their annual income and hours spent online per week. The distance measures calculated from raw data can be distorted because the annual income values are much larger than the values of hours spent online per week. We can use z-scores or min-max transformation to standardize the observations. To calculate a z-score, you first need to find the mean and standard deviation for the variable you want to standardize. Then for each data point that you want to standardize, you will subtract the mean from that data point and divide the result by the standard deviation for that variable. To conduct a min-max transformation, you first need to find the min, max, and range values for the variable that will be transformed. Then subtract the min from the data point that will be transformed and divide that result by the range for that variable. Euclidean and Manhattan distance measures are suitable for numerical variables. For categorical variables, we rely on other measures of similarity. A categorical variable with only 2 categories is called a binary variable. 2 commonly used measures for categorical and binary variables are the matching coefficient and Jaccard's coefficient. The matching coefficient for a categorical variable is based on matching values to determine similarities. The higher the value of the matching coefficient, the more similarity. A value of 1 implies a perfect match. Consider the list of college students with their major, field, sex, and whether or not they are on the dean's list. We can compute the matching coefficient between all pairs of students to determine how similar or dissimilar they are from each other. For example, when comparing students 1 and 2, only one of the 4 variables, the dean's list, has a matching outcome. Therefore, the matching coefficient equals 1 out of 4, 25%. The matching coefficient makes no distinction between positive and negative outcomes, which may provide a misleading measure of similarity. Jaccard's coefficient ignores negative outcomes and provides a more accurate measure of similarity for binary variables. Let's take a look at an example. A retail store collects point of sales information showing whether or not 5 products were included in each sales transaction. We can compute and compare matching coefficients and Jaccard's coefficients for all sets of pairwise transactions to determine similarities. To compute the Jaccard coefficient for transactions 1 and 2, first count the number of matching outcomes. There are 2 positive matching outcomes, keyboard and mouse, as well as 1 negative matching outcome, USB drive. The coefficient for the pair is calculated by taking the difference between total number of variables 5 and subtracting the number of negative matches 1 and dividing the result by the number of positive matches 2 for a coefficient of 2 out of 4 or 50%. This concludes the lecture on similarity analysis. Thank you for your attention.